Hello learners, in this class we'll discuss design of two-flight staircase. Generally it's called a dog-legged staircase. We'll discuss the problem and the codal provisions will be discussed while going through the problems solution. Now, design a two-flight staircase with steps on west slab. West slab means if you might have seen this your staircases. So if the staircase is going like this way, then these are the steps on these stairs, and this is called the west slab. So this slab is called as the west slab. For floor to floor height of 3.3 meter, the floor to floor height means that is, this is a floor, this is a floor. So landing to landing, this is a landing, this is a landing. So floor to floor height is given 3 meter, 3 meter height floor to floor. Width of the flight is 1.15 meter. That means this width is given 1.15 meter. Okay, width of the flight this side, and superimposed load is 3 kN square. The load is more in case of depending on whether you are using for residential building or for the commercial complexes or school buildings, hospital buildings. So depending on the type of building, this load will also increase. Now the support condition is given simply supported on landing slab which span transversely to flight. So flight is go like this way. So transverse to this goes to the your landing. Using M20 and FE415 design the staircase. Basically these are all slabs. They will be designed as a slabs. Only the loading pattern you have to find out, but the loads coming to the slabs, and these slabs are horizontal slabs and this is the inclined slab. So if you take projection on the horizontal span, then loading should be converted perpendicular to the span. And once you find the loading, you can find the maximum bending moment and maximum shear force, and design will remain just like a slab design. Let us see the details of the design procedure. Now all the clauses, tables and graphs as per IS 456-2000, and height is given 3300. So that means you have to find the number of steps, what the number of steps will come. So and what the rise, what is the trade. So if you take the slab, so this is called the trade, and trade this is called the rise. So generally rise is taken 150 to 200 millimeter, and the trade is taken 250 millimeter, 300 millimeter, like that. So it is given M20 is FCK is 20 Newton per millimeter square, lime load 3. So we assume the depth or thickness of the slab 200 millimeter, cover is taken 25 millimeter, minimum cover is 20, and 10 mm bars are taken, and rise is 150 and trades 250. So this also you have to assume. You have already been studied regarding these staircases in your construction technology or somewhere else. So these are the standard things. You have also designed these sizes and this dimension of this staircase. How to choose the dimension is also known to you earlier in your early semesters. Now once you assume these values, rise, trade and diameter of rods, then find the calculation of dimensions. So how many rises will there, how many trades will there, then what is going, so that you have to find. So number of risers will be, you divide the total height, floor height by 2 is called height of the flight, that's called each flight. So if you divide the 2, then it will be 1650 is the height of the flight. So 1650 divided by 150 is the one rise. Total rise is 1. So number of rise minus 1 will give number of trade. And if you multiply this number of trade with the width of the trade, then you will find out the going. So this distance, horizontal distance, will find is called as the going. If you go like this way, go like this way. So projection of all these things, if you combine this now up to, if you add all these horizontal distances, so this will be called as going. So going is equal to this number of trades multiplied by the trade width. So trade width is taken 250, so it comes 2500. Now what is the effective span? Effective span, how to calculate? It is given on the IS code. So please open your IS code. 456, page number 63. So here it is given the stairs. The clause number 33 give the stairs. So what is the effective spans? The effective spans are given for different conditions, but the clause B, I'm not going detail of A and C. Depending on the other type of staircase you are going to design, the effective span will be different. So that is generally center beams. If they are if it supported top and bottom risers by beams spanning parallel to risers, the distance is center beams. Also in this case, C is taken as the slab spans in the same direction of the stairs. They shall be considered acting together to form a single slab, and the span determined at the again center to center of the supporting beams or walls. But in dog-leg staircase, where the spanning on the edge of a landing slab which spans parallel as shown in figure 17, a distance equal to going. Distance equal to going. We have already calculated going upstairs. Plus at each end either half of the width of this landing or 1 meter, whichever is smaller. That you have to find out. So let us see the figure given below. For this figure given below, just go to this figure now. Now in this figure, what is given? Now this to this is going. So going is from here to here. We have already calculated. Now they will be landing this side. They will be landing in this side. So half of this or 1 meter. This side half of this or 1 meter, whichever is less. It cannot be more than 1 meter. Okay. That is why every one is less than 1 meter, both are less than 1 meter, then G plus X plus Y. X is this side, Y is this side, half of this side, half of that side. And if all the conditions are given here, if both are more than 1, you have to take G plus 1 plus 1. But this condition will again change if you have an entrance. In the entrance, there is no landing. So one side will be absent. It will be only going plus one side, half of the other side. Okay, are you able to understand? While entrance, in the entrance, there is no landing. You are calculating landing to landing. If there is no landing, that side half will be omitted. So other side you see half of this plus going. That will be the effective span. So if you find the effective span, then you can multiply the loadings and find the moment and shear force. Now, how the load is distributed? In case of stairs with open wells where spans partly crossing at right angles occur, the load on areas common to any two such spans may be taken as 1/2 in each direction. Figure 18. So some loading conditions have been shown here. You see, the next page you go. Loaded stairs with open well. If we have not open well, we have dog-leg staircase, and you find the if you have these landings will be different loading, and these if you have this open well, these stairs will be W/2 if the loading here is W. So it is shown here, and if people take cross section like this, loading while calculating this effect, this span on this going it will be W, and on this landing it will be W/2. While calculating other side, this is the main stair, so it will be W here, and both side landing will W/2 W/2. So this is the condition for the open well type. So we'll see in dog-leg staircase how we calculated in our present case. Now depth of section shall be taken as the minimum thickness perpendicular to soffit of the stair. Soffit of the stair means that means you have this stair like this. Okay, so perpendicular to this distance will be taken as the thickness of this slab. So let us again go back to our problem. Now, so now what is going here? One find the going effective span is both sides you have 1115 and 1150. Where in the problem it has given that the width of flight is given here 11150. So half of this and half of that on both sides, which will give the value of effective span. Effective span is equal to 2500 is the going, plus 1150/2 is less than 1 meter, and 1150/2 is also again less than 1 meter. So it is 3650, or 2500 plus 1000 and 1000, whichever is less. So generally it is coming less. So 3650 is the effective span, and the effective depth will be your overall depth minus cover minus half of the diameter rod. It comes out to be 170 millimeter. Now you see, now this is our case. In this case, we have 1150 here, 1150 here, and going is 2500. You going from this side, then this side landing to landing. Okay, landing to landing you are going. Then you find the this is one of the intermediate stairs. It is not the entrance or not on the end point. You are going from one landing to other. So you have different floors. It is one of the intermediate floors. If you with the ground floor or the top floor, then it will be different, because in the front floor there will be no landing here, and also in the top floor there is no landing there. So one side will be absent. Now next we will go to, once find the effective span, we will find the loads. How the load will calculated? So one is the dead load and live load, and there will be floor finish if you can take floor finish. But because these stairs will be there on the slab, if it is your slab, then there is your steps. So on the steps you are moving on steps. So one is the load of the step will come, and then dead load of this inclined slab will come. But the load in the inclined slab will act perpendicular to this slab. But the span is taken like this. So you have to find the component of this along this direction. So you have to find the component along the vertical direction. So that is gamma d cos theta. Gamma is the unit weight of concrete, 25 kilonewton per meter cube. D is the overall depth of the slab. So you find cos theta. What is the cos theta? Now if you take this is your situation. Take one of the section. So now this is T, this is R, and this is your root over T square plus R square. So now this is the theta. The theta is equal to cos theta. So R square T square by T. So you find the component of this along this. So you'll find the value of theta here. So this becomes theta, and this is theta. So you can find the value like this way, the component. So find this value, 25 into 0.2, and then the values, the double square, there will be 1 square basically. So you omit 1 square. So this value is come 5.83. Now the self weight of step, will be half trade into rise into unit weight. So if it is made of brick, it will be different. If it is made of concrete, different. So it is concrete, so trade to rise. And this is the concentrated load. So per meter width means you have to divide with again trade. So load per meter length, because we have to find the UDL. So again, you know, in the slab it is per meters per you're taking 1 meter width of this, 1 meter width of the slab. So it is load in kilonewton per meter. So here we will find the total weight of the steps per trade. So again divided per meter width. So divided by trade. So that comes out to 1.875. Superimposed load is given 3 kilonewton per meter square. Then add all these values. So it becomes 10.70 and multiply 1.5 to find out the factor load. So now 16.05 kilonewton per meter square is the loading on the slab, inclined slab. The projection, the slab is taken going is horizontal. So the component of all the loads perpendicular to this horizontal span, it comes out to be 16.05 kilonewton per meter square. Now what is the load in landing? Because we have seen that one is this your going and one is the landing. So one is the slab is going like this way, then like this. So here is coming like this. So this is the landing, and this is also landing. So what is the load on landing? Because this is taken horizontal projections by going. Then this is the landing, and this is also landing. So you have to also find the load on the landings. So load will dead load. So again 0.2 is the depth. Then live load, and total load becomes 8, and the factor is 12. So 12 kilonewton per meter square load will come on this landing portion, and 16.05 will come on this flight, or you will find on this going. Now you have to find the bending moment, maximum bending moment. So draw the bending moment diagram. You have to draw the bending moment diagram, how the load is acting now. So you come to this, you have already been taught this your force bending diagram for the simple supported slab. So both are simple supported both sides. 2.5 meter is this your 2.5 meter is your going. Then half on both sides. You cannot take the entire landing. Half of the landing on both sides. The center to center you have to take. So this is 0.575 and 0.575. Here is 12 kilonewton meter, 16.05 kilonewton meter. So find the reactions, that will be the shear force, and find the maximum bending moment which may occur at the center or somewhere else. So basically it will be symmetrically loaded, so the maximum bending moment is center. So you have to find out the maximum bending moment and maximum shear force for this problem. So we find this is being taught in your strength of material or analysis of structure. So I'm not going detail of calculations, but the moment is coming 26.057 kilonewton meter, and this shear force is reaction. So reactions comes out to be 26.92925 9625 kilonewton. Both will be required for the shear calculation and bending calculations. And so once you find the maximum bending shear force, then you have to check for depth. Again, depth for check is equal to the maximum bending moment is equal to ultimate moment mu limiting, and mu limiting is equal to r into r bd square, and r is the value for M20 and Fe15, it is 2.76. We have already discussed, and so d is comes out to 97 millimeter. So we have taken 200 millimeter, so it is coming 97.16. Our effective depth was 170 perhaps. What the effective depth? 170. So against 170, we are getting 96. So it is okay. 96 millimeter, 97 against 170. It's not 200. This will be 170. Correct it. So this value is basically 170. That is effective depth. So this value less than that, so it is okay. So now find out the area of steel. Again, B is equal to slab, B is equal to 1 meter. You see B is equal to 1 meter, and D is equal to D provided, that is not 200, it should be 170. So there are slight corrections here. So make the calculation change, because we have taken D is 170. Now this value comes out, if it is 200, it comes 375. It will change accordingly. So once you find AST, find the spacing of 10 mm diameter bar. So that is equal to 1000 pi by 4 pi square. By the area, it is 209. So provide 200. So it will take 3D or 300 millimeter. So that is more. So it is we provide 10 mm 200 center as the main reinforcement on the flight. And the distribution steel will be equal to, again the minimum steel we have discussed, at 0.12% of the cross area. And using 8 mm parts as this reinforcement, you find the spacings come 180. So provide 180. So the distribution steel comes 180, and this main steel comes. So main steel. Suppose you provide the main steel is coming 10.5, and then distribution steel come on like this. So this is the main steel and the main steel, and this is the distribution steels. This is the main steel. This 10.5 at the rate of 10 pi at the rate of 10 pi at the rate of main steel is coming 200, 10 pi at the 200 center, and distribution steel is coming 8 mm 180 center. So this is the 10 mm 10 mm at the rate of 10 mm at the rate of 200 center. We'll see the drawings, and here you will find the 8 mm bars. So this is the reinforcement detailing will have to find out. Then after doing this detailing, then you have to find a check for shear. So again, tau b should less than k tau c, because it is a slab. So find out your load where this vu is equal to shear at a distance of 200 millimeter. Effective distance we have seen the critical sectional distance d from the face of the support, or you can take at also face of support. If the time is very less, you can take directly 20.06. Calculations details. You find out this maximum shear reaction was 26.96. So 26.96. This is there's some error here. It is 26.96. Please change it. 26.96. So either you calculate this value, or you can take the maximum value 26.96 and calculate B into D, and then find the percentage of steel. So taking all the steels into support, you find all this percentage of steel 100 AST by BD, and then find tau C from the table number 19. Then K tau C. K again depends on the depth of this slab, which is 200 millimeter. So see that chart, it varies from 100 to 300, and accordingly find the value of K. And tau B less than K tau means there will be no shear design is required, or no shear reinforcement is required. So once you check the shear, you can also check for development length. Then LD is equal to 0.87 Fy 5 by 4 tau BD. Similar way, 60% again increase for these torque steels, and you find out the total moment you have already obtained and shear force you know, and then plus L0. L0 is equal to half of the support minus the cover. So the width of support you may take 300 millimeter. That slab is entered inside the wall, so that is equal to L0. So you find LD is greater than LD is less than this 1.3 m by V plus L0, because it is simply supported at both ends. So they will produce, the reactions will produce compression. So that is why 1.3 is multiplied for the calculation of the m by V. So once the check for development length is completed, then you can go for the detailing. Now you see the detailing part here. So these are the main steel, as I have indicated earlier. These are the main steels. So main steel is 10 phi 200 center, and these bars are 8 phi 180 center. And you can also provide the same steel in the landing portion. Or if you want, you can also design the landings separately, and the reinforcements can be obtained and put on the landings. But generally, these rods are goes and extended here, and this steel comes and go inside this plate, and this main rail from plate go to the landing on the top. Also, and the other same side you have to do. So this is all regarding this design of doglegged staircase. There are also different cases for the design of other type of staircase, for which you have to very carefully find out this bending moment, loading pattern, and the effective span. Then it is designed as a just like a slab. So with this we conclude the lecture, and have a nice day.